talk will begin shortly. Yeah, please be advised to stand by. Okay, Dr. James, you can try to share your screen. Okay, great. I can see clearly.
Excellent.
Okay, so we are going to start now. Ladies and gentlemen, we are honored to have Dr. James Saga, Strategic Product Manager of Oxford Instruments Magnetic Resonance in this sponsor talk. So Dr. James Saga is representing PLT Scientific to deliver a talk on the optimizing battery electrolyte performance and quality with benchtop NMR. So if you have any questions, please send your questions to the presenter via the Q&A function in Zoom, as well as the comment function in our YouTube. So all questions will be addressed by the end of this presentation. So without further ado, please welcome Dr. James Saga.
Thank you very much for that kind introduction. This morning or this afternoon, I'm going to talk to you about optimizing battery electrolyte performance and quality with benchtop NMR. So first of all, I'm going to give an overview as to what benchtop and broadband benchtop NMR is and how that relates to battery electrolytes. I'm going to give some examples of applications in quality control, how we can use benchtop NMR to understand decomposition of battery electrolytes, and then how we can use that same instrument to optimize key electrolyte performance characteristics. So first of all, broadband benchtop NMR, what is it and how does it relate to battery electrolytes? Well, I'm sure most of the people here know what NMR is, but it's always good to have a little refresher. So NMR spectroscopy is based on the idea that certain nuclei have a non-zero spin. That's where our nuclear comes from. In our bulk sample, there are many of those spins, all randomly oriented. When we apply a large external magnetic field, we can align a proportion of those spins. That's where our magnetic comes from. And once we have those spins aligned with the magnetic field, we can start to do interesting things by exciting them with a radio frequency pulse. That starts to rotate the magnetic moment, giving us our resonance. That rotation induces an electric current in our pickup electronics, and as we remove that RF pulse, that signal decays. This is what we know as our free induction decay. We can go round and round that loop of excitation and relaxation to increase our signal and average out our noise. At some point, we can then Fourier transform that acquired data to give us our NMR spectrum that most people are familiar with. The difference usually between NMR and benchtop NMR is sort of what I'm saying there. Normal NMR instruments use a large superconductive magnet, usually in a building on its own, whereas a benchtop NMR system fits on the bench in your lab, or could be installed in a fume hood or even a glove box. We take the same design philosophy for our instrument, the X-Pulse, as a high field instrument, separating our magnet and our electronics console. And there in our magnet, we have a large permanent magnetic field, about 1.47 Tesla. And what that means is that you can just drop your sample straight into the top of the instrument on the bench next to you while you're doing your chemistry. Now, there are a couple of key performance criteria for a benchtop NMR system when measuring electrolytes. You need to be able to put it on the bench, which means it needs no liquid cryogens. It needs to operate at normal room temperatures. Really, you don't want a dedicated operator. It needs to be used by anybody who has access to the instrument. It needs minimal stray field, and it needs to be of a size and weight that means it can be placed on a bench or in a glove box. In terms of performance, it needs to have the resolution, sensitivity, and stability to deliver the results you need. You also need to be able to analyze all the relevant nuclei for your electrolyte, as well as applying pulse field gradients, which I'm going to talk about later, and potentially measuring over a range of temperatures. So the X-Pulse, our benchtop NMR system, has a very high resolution of less than 0.35 Hertz at the full width at half height. That allows us to resolve complex proton spectra at low field. We also are the only benchtop NMR instrument with a truly broadband multi-nuclear capability. That means that we can collect spectra from a wide range of nuclei present in electrolytes. So lithium, fluorine, phosphorus, boron, sodium, hydrogen, and carbon. We can equip that instrument with a variable temperature system to evaluate those electrolyte properties over an extended temperature range. We have pulse field gradients to measure diffusion, and it can be installed on the bench in your lab. So let's come round to batteries. So here is a typical cross-section of a battery. We know we have our anode, cathode, and between those two, we have an electrolyte. In most common battery systems at the moment, that electrolyte is a combination of organic solvents, usually cyclic carbonates, and some potential additives, and a lithium salt. In most cases at the minute, lithium hexafluorophosphate. Now, when we're thinking about batteries and optimizing their performance, usually people tend to talk about 5 potentially competing factors. So energy density, how much energy can be stored in that battery, the power density, how quickly can we use that, safety of the battery, the lifespan, and the cost. And when you put a few common chemistries, so nickel, manganese, cobalt oxide, or nickel, cobalt, aluminium oxide type chemistries, then you can see the difference in those performance characteristics. And it's not just by optimizing the electrodes that we can increase our performance. You can also optimize the electrolyte to deliver the same sort of thing. So if we look at where X-Pulse can help across those key performance characteristics, we can look at energy density by measuring salt concentrations. We can look at power density by measuring diffusion coefficient, allowing us to measure things like conductivity and transference numbers. We can ensure safety by measuring electrolyte quality or developing additives in electrolytes. We can understand the lifespan of a battery by understanding electrolyte breakdown, and we can decrease the cost by allowing rapid analysis of new formulations, decreasing your development costs, and also reducing that cost of poor quality. So here is a few applications in quality control. So here's a little case study. A company approached us to support their quality control of typical electrolytes, and they had a few key questions for us. Can benchtop NMR accurately determine salt composition? Can it quickly identify poor quality material? And can battery NMR or can benchtop NMR provide insights as to why my material failed? The company provided us several samples, all nominally described as lithium hexafluorophosphate in a combination of dimethyl carbonate, ethylene carbonate, and diethyl carbonate. And obviously, we start with NMR, and we always take a hydrogen spectrum. It's the quickest, most sensitive nucleus, and we tend to use it to just see what we have in our sample. And you can see here, these electrolytes, these cyclic carbonates, tend to give us quite nice, simple NMR spectrum. So we can resolve all the signals very nicely. We have our signal here from our diethyl carbonates, the quartet here, and the triplet here. We have our singlet from our dimethyl carbonate, and we have our singlet from our ethylene carbonate. We also have a small signal at a higher chemical shift here for our ethylene carbonate additive, which is typically added to these formulations to form a robust SEI layer. And by the wonder of NMR being an inherently quantitative technique, that means by measuring the integrals of these signals, which are noted here below the spectrum, and understanding the molecular weight of those compounds, we can understand exactly their weight percentage composition in that electrolyte. That's an incredibly powerful tool to ensure the quality of electrolyte. We can also use that same technique to ensure that as we're developing a formulation or we're continuing our quality control, that we have the right sort of additives in there. So from those spectra, we see there are 4 here with varying quantities of vinylene carbonate. The rest of the concentration is essentially identical. But again, NMR is inherently quantitative, so we can quantify the vinylene carbonate concentration down to sub 1%, sub 1 weight percent. And that's critical for these applications because for that vinylene carbonate concentration to be effective in that electrolyte, it needs to be somewhere between 1 and 2%. Now, we were also given another challenge. So a question of what's wrong with my electrolyte. We were given 2 samples that were supposed to be the same chemistry, lithium hexafluorophosphate in ethylene carbonate and ethyl methyl carbonate. But when placed in a final cell, there was an observed difference in the performance. So both were colorless liquids, quite difficult to test what the differences were. So what was that difference, and could benchtop NMR give us the answer? If we go straight to that proton spectrum, as we've previously done, we can see that actually their proton spectra look exactly the same. We see our singlet from our ethyl methyl, from our ethylene carbonate, our small vinylene carbonate peak, and our signals from our ethylene carbonate. So the ethyl signal here, and then the 2 methyl signals. But there's no difference between those 2. So clearly, all this signal comes from the solvent. So there's no difference in the solvents. We have to look elsewhere for the root cause of this failure. So we go to fluorine NMR, the second most sensitive NMR nucleus. And immediately, the issue becomes obvious. Between the 2 samples, the bottom sample and the top sample, we see that we have a doublet here that corresponds to the splitting of these 6 identical fluorines or equivalent fluorines by the phosphorus in this nucleus, or in this molecule. But in this top spectrum, we also have a second doublet. Now, that's most likely a breakdown product from some parasitic reaction, and that means that you've not got the same salt concentration. Potentially, you've got other contaminants elsewhere that we can't see or that have dropped out of solution. And that gives us a great understanding as to why this issue of performance may have taken place. So we know that the PF6 salt has broken down, mostly likely through a common hydrolysis reaction path. And we can observe signals in actually not just the fluorine, but the phosphorus NMR as well. And that would suggest the presence of a phosphodifluoric acid. So clearly, we know not just that the electrolyte has degraded in performance, we know why it's degraded in performance, and we can understand exactly why that degradation of performance has happened. So let's have a look at those decomposition paths. Well, common electrolytes can take a lot of different decomposition routes, and understanding these is key to developing safer, longer life batteries. Now, I've spoken about that hydrolysis path here, which is what we'd experienced before, but you can also look at polymerization of those cyclic carbonates. Those are another degradation path. But I'm just going to focus on that hydrolysis path for now, and what we can do with benchtop NMR to understand that in more detail. So by adding a small amount of water to a commercial electrolyte of lithium hexafluorophosphate in dimethyl carbonate, we can force this hydrolysis reaction to take place. And we expect to see this, a degradation of this lithium hexafluorophosphate into some lithium fluoride and PF5, then a further reaction forming water and hydrofluoric acid into these phosphodifluoric acids. So we collected fluorine spectra, 19F spectra, every 30 minutes to track the reaction progress. And the results are quite obvious. We take the red integral of this signal and the yellow, green, purple, and blue. Red corresponds to PF6. The yellow and green correspond to these two phosphofluoric acids. Purple shows us the concentration of hydrofluoric acid, and lithium fluoride shows us the buildup. The blue shows us the buildup of lithium fluoride. And you can see that after adding the water, the reaction occurs very quickly. We get a large drop in the PF6 signal, a large increase in the lithium fluoride signal, which we see is essentially the first part of this reaction. But this PF5 must be very short-lived, as we don't tend to see a signal for it. And as we continue over time, we see an initial buildup of phosphodifluoric acid, and then a breakdown into phosphofluoric acid. And that's clearly very useful for understanding these decomposition paths. One thing that's also very useful is if you take a step away from that end of process when you're optimizing your quality and trying to understand how your quality can deteriorate, is how you can actually develop electrolytes and how you can optimize their performance through through their development. And one way that benchtop NMR can assist that is using pulse field gradient NMR. So obviously there are many different parameters that can be modified with existing electrolytes. However, the ionic conductivity, viscosity, and transference are crucial to understand how that may perform in the final cell. So being able to measure a wider range of parameters, such as the diffusion coefficients, as well as transference numbers, can give us a much better understanding of exactly what that performance might look like. And we can do that with pulse field gradient NMR. Now, this particular NMR experiment essentially uses a set of gradient pulses, so separate from the main RF pulse, to dephase the signals that we get according to the diffusion coefficient of the molecules within our solution. So as we increase the strength of these two gradient pulses here in blue, we see a decrease in the signals in the spectra, because there is a decrease or there is a dephasing of those signals. So less of the spins contribute to our peak intensity. Once we've got this decrease in the signal, we can use this statistical-Tanner equation here to, by plotting this, we can get a graph where the negative of this gradient here is directly the diffusion coefficient, d NMR. Once we have that diffusion coefficient, we can use that for the anion and cation and anion to calculate the ionic conductivity or the cation transference numbers. Now, in principle or in practice, what does that look like? Well, here we have some results taken at 40 degrees C of a proton spectrum, a fluorine spectrum, and a lithium spectrum. And you can see that these are stacks of spectra collected at different gradient strengths. As we increase that gradient strength, we see a decrease in the signal in all cases from that dephasing. And from that decrease, we can plot that statistical-Tanner equation, getting our linear response, from which we can read off our diffusion coefficient. We can see two slightly different diffusion coefficients for our two cyclic carbonates. in our solvent. We see the hexafluorophosphate anion has a different diffusion coefficient again, and then our lithium signal for our lithium cation again has a slightly different diffusion coefficient. And from these we can calculate the anion conductivity of that electrolyte as well as the transference number. This is the cation transference number for a lithium electrolyte. We'd really want that to be as close to 1 as possible. Here you can see it's about 0.4, so not necessarily the best electrolyte that you would want in your final cell. What we did, and this was some work we did with the University of Oxford, was to understand how or whether we could measure this performance across a number of different electrolyte formulations. Now, these are similar to those typically used in commercial cells. So 3 of the samples used a lithium hexafluorophosphate lithium salt, and we had 1 sample that was dimethyl carbonate, 1 sample that was a 50-50 mix of dimethyl carbonate and ethylene carbonate, and a 3rd sample that was in propylene carbonate. A 4th sample was TFSI in tetraglide, typically much more viscous polymer, almost liquid polymer electrolyte, which is used in some new battery formulations, particularly ones with maybe a lithium anode. And you can see quite significant differences in these statistical Tanner plots. So these plots plot the log of the intensity divided by the intensity at 0 gradient strength versus this set of constants down here. And as I said before, that means that the negative of this gradient here is the NMR diffusion coefficient. You can see that in all cases, we have a varying set of gradients or diffusion coefficients for the different molecule species or nuclear species within our system. So in this case, the lithium and fluorine and phosphorus responses are very similar with very different proton diffusion. There is a wider range when we look at the dimethyl and ethylene carbonate. In the hexafluorophosphate and propylene carbonate, we see quite different to the dimethyl carbonate that the lithium has a certain response, and actually the fluorine and proton have very similar responses. The TFSI and tetraglide has a very different diffusion coefficient overall. As I said, it's much more viscous. We'd expect less diffusion, much larger molecule. And this gives us very similar to the response that we would expect. So if we summarize all of that, then we can see that we have quite big differences in our conductivity across those 4 different electrolyte formulations and quite big differences in our cation transference. What's also useful is that you can use this pulse field gradient NMR to understand the effect of that decomposition on our electrolyte, not just understanding how an electrolyte is decomposed, but actually how that might affect its performance when you put it in a cell, or if the electrolyte was to decompose in the cell, how the performance could be affected. So the eagle-eyed of you may have noticed that when we did that reaction series, there was actually a gap between 40 and 80 minutes of collection. What we did during that was to take a pulse field gradient NMR experiment. And you can see that after that exposure to water, there is a significant difference in the diffusion coefficient of that, in this case, the fluorine or the hexafluorophosphate anion. Big difference in the diffusion coefficient. That means you're going to get big differences in the ionic conductivity and the transference. So that's exactly where that performance decrease that was seen by our customer was coming from. The fact that you get less diffusion, you're not as efficiently transferring charge, and therefore the performance of your cell decreases. So just to conclude, where can benchtop NMR assist with electrolyte analysis? Well, in terms of raw materials, we have relatively simple proton spectra, perfect for benchtop NMR, that allow us to measure in minutes the quality of our raw materials, whether that's our raw material solvents or whether our raw material salts or additives. And we can quantify the key parameters that ensure good product from our electrolytes. In an R&D environment, we can get almost instantaneous feedback on new formulations. We can ensure that we're making what we thought we were making very quickly, and we can also use diffusion experiments to unlock the physical properties of those electrolytes. Further to that, again, we can expand that ability to perform quality control on these materials. We can ensure the quality of final product. We can determine what components are there, if there are any contaminants, and if we're seeing breakdown products. And because NMR is that chemically specific, we can understand whether they may be contaminants coming from poor raw materials, whether they're a breakdown of the current material that you're getting, or whether it's a foreign contaminant completely to the expected reaction. So thank you very much for listening, and I'll now take some questions.
Yeah, Dr.
Okay,
Dr. James
thank you,
Saga.
Dr. James.
Yep. Yeah, I'm Gan here. So there's one question from the floor. Dear Dr. Saga, just wondering, how does benchtop NMR compare with traditional MMR, for example, 300 megahertz?
So obviously the main difference is the field strength. When you go to lower field strength, your field dispersion of your spectra is lower, and your sensitivity is also lower. But that doesn't mean that you can't get the same information out of those nuclei. All the same information is there. Sometimes you just have to use a little bit more maths potentially to get some of that information out. Actually, in a lot of the cases, and in specifically for these battery electrolytes, the difference between a 300 megahertz spectrum and a benchtop NMR spectrum is almost non-existent. They're very simple spectra. You can get all the same information that you would from a 300 megahertz instrument.
Second question, any limitation to the type of deuterated solvents usable in benchtop NMR?
No, we can use deuterated solvents, but also the other thing about benchtop NMR is we can typically use non-deuterated or protonated solvents as well. We have both an internal deuterium lock and an ability to perform a locked experiment without deuterated solvents.
Yeah, the following question is, does this mean you will require more concentrated sample preparation to counter the sensitivity you have previously mentioned?
It would depend exactly on your application. In the context of these battery electrolytes, then they're exactly as you would buy them from a supplier. They're incredibly concentrated anyway. If they weren't, they'd be pretty poor electrolytes. In a wider context, then yes, for small molecules, pharmaceuticals or something, then you would typically want slightly higher concentrations. If you're using a proton NMR and you're only interested in proton NMR, you want to be using something like more than probably 20 or 30 millimolar concentration. For carbon NMR on the same system, you probably want to be using at least 150 millimolar to ensure you're getting data in a reasonable sort of acquisition time.
Yeah, I have one personal question to you. My field is more on like material science in solid state, working on dielectric devices in solid. So I come across using like glycolytic based material with high conductivity. So, and we use impedance analyzer to measure the thin film, and then we measure the capacitance value, and we convert to the diffusion coefficient using the formula you just mentioned just now. So, yep. in comparison to the impedance analyzer we use and into the MMR, and we've realized that actually the value being evaluated is more or less the same. But for your material, for your actual instrument here, MMR, I'm a physicist. I'm not so sure on this aspect. If we use less conducting polymer for MMR measurement, so will it work to calculate to be able to evaluate the self-diffusion coefficient?
Yes. So that's a so that will depend exactly on your NMR system and the diffusion coefficient or the self-diffusion coefficient of your material. With the X-Pulse instrument, we typically use liquid state samples or solution state samples. We can get down to a self-diffusion coefficient of about 10 to the minus 12, maybe 20 to the minus 13 at a push. For more solid samples, you probably can do it. What we would do with our instrument and our range of instruments is we would actually move to what we call a time domain NMR instrument with pulse field gradients. There we get about 10 or 100 times the gradient strength.
So
that means that we can
domain. So sorry to disturb. The time domain is just using the fast Fourier transform to convert the frequency to the time domain, or just we have to specific hardware to do it.
No, you can. I mean, we would supply we would supply relaxometers, lower dead times. You can see more of the solid component of your sample, but actually, essentially, you're just not doing your Fourier transform. If you want chemically specific, then you might want to do your Fourier transform. But as long as you can get sufficient gradient strength, then you should be able to measure your self-diffusion coefficient. 10 times the gradient strength, 2 Tesla per meter, something like that, will get you down to a diffusion coefficient of about 10 to the minus 16, which will do most of your polymer electrolytes, may get you into some of the range of some of the sulfides, and potentially even some of the perovskite and garnet type electrolytes.
Okay, thank you very much. So if there's no other question, okay. Thank you, Dr. James, sharing your insightful information with us for the MMR machine. So MC, shall I pass the stage to you now?
So thank you, Dr. James, for the very informative talk. And to all the audience, if you have any further questions, you may either email to Dr. James or PLT Scientific directly. Yeah. And on behalf of ICEM 2021, I would like to extend my sincere gratitude to PLT Scientific Sdn Bhd for making this conference possible. And ladies and gentlemen, our sponsor talk from PLT Scientific will end here. And for our, we have our parallel symposia EM2, EM3, and EM4 are ongoing now in Hall A, Hall B, and Hall D. So please refer to our program handbook for the Zoom link to the respective EMs. And we hope to see you later. Thank you. Bye.
Thanks a lot, Dr. James.